Hi class, we are going to pick up where we left off on page 19, and this is example 10 in our notes, where we are trying to discover what is the molarity of pure water, which is to say, what is the molarity of water in water? What is the molality? You can assume 1 liter of volume here, and at 25 degrees, the density of water is 0.9970749 grams per milliliter, but we're going to use fewer sig figs than that. The molarity is described as moles per liter, so we need moles given that we already have liters. And from the periodic table, we can figure out that water has a molecular weight of 18.015 grams. So we can calculate how many moles of water we have. So we take 1 liter, multiply by a conversion factor of 1,000 milliliters per liter so that our liters cancel, and then we multiply by the density of water, which is 0.9971 grams per milliliter, so that our milliliters cancel. We can then convert from grams of water to moles of water by dividing by the molecular weight. If you're ever unsure of whether or not you want to divide or multiply, just make sure that your grams of water are canceling with grams of water in the denominator. So numerator and denominator should be canceling, and what we're left with is moles. So after you essentially do 0.997 times 1,000 divided by 18.015, you get 55.3 moles of water. Now we have defined that our volume is 1 liter, so molarity is nice and simple now. It's moles per liter, and we have 55.3 moles divided by 1 liter, so our molarity of water in water is 55.3 molar. Now we can solve for molality. We take that 1 liter of water, multiply by 1,000 mils per liter, and then multiply by our density, 0.9971 grams per milliliter, and we're left with, so far, grams of water. We then convert from grams to kilograms by doing 1 kilogram is equal to 1 gram. Again, if you're ever unsure, we must have our grams in the denominator so that they can cancel with our grams in the numerator over here. And the 1,000 goes with grams because there's 1,000 grams per 1 kilogram. We do that math out and we end up with 0.997 kilograms of water. And so to figure out the molality, that's moles per kilogram, we already have calculated the moles earlier, and that's 55.3 moles divided by 0.997 kilograms, and we have our answer over here on the side since we ran out of space, and our molality is 55.5 molal. So on the bottom of page 19, I included an additional piece of information, and if you have space left, great. If not, you can go on to page 20 where you should have an extra blank page for notes. So here, under the title Vapor Pressure and Intermolecular Forces, we are describing the trend of how intermolecular forces relates to vapor pressure. And the trend is as follows. The weaker the intermolecular force, the greater the vapor pressure. Again, the weaker the intermolecular force, the greater the vapor pressure. And here's why. If you take something like water, water has a dominant molecular force of hydrogen bonding, so that's a strong intermolecular force, IMF, which means it has low vapor pressure. So if we have the liquid phase down here, and that's water, that's all stuck together by a really strong intermolecular force, hydrogen bonding. So in the gas phase, we don't have that much water, considering, because most of it is still stuck together. So it actually takes quite a bit of energy to break up those bonds between water to get water into the gaseous phase. Now, hydrogen bonding is one of our stronger intermolecular forces. Going a little bit weaker to something that is an example of a dipole-dipole interaction, we describe these in chloroform. If you recall, chloroform has this tetrahedral shape. Each of these carbon to chlorine bonds are polar covalent bonds, and the polarity is going towards the chlorine. So this molecule is asymmetric and has an overall polarity going vertically down. So this is a polar molecule, but it's not capable of hydrogen bonding, so its dominant intermolecular force is dipole-dipole. So this is a weaker intermolecular force, so the liquid phase is stuck together less, which means that at a certain temperature you have more gas phase chloroform than you would have gas phase water. So that is a weaker intermolecular force creating a greater vapor pressure. And then finally, we go to an example of the weakest intermolecular force, which is dispersion forces, which we see in nitrogen gas. This has no liquid phase at all, because this is a very weak intermolecular force, which gives it a very high vapor pressure. Dinitrogen barely sticks to itself at all, so it's all in the gas phase floating around. We're going to continue our discussion in properties of solutions with colligative properties and discuss how the presence of a bunch of solute in a solution changes the physical properties, for example, boiling point. So the vapor pressure of a solution is lowered due to the presence of non-volatile solutes. The boiling point of the solution will subsequently be increased. Now I'm going to include the definition here of boiling. The boiling definition is when the vapor pressure of your liquid is equal to the atmospheric pressure around it. So if we take a look at a situation where we might have pure water boiling, these slides are going to be posted to OnCourse. So if we have a pure water boiling, we have a certain amount of vapor pressure of water above the surface of the liquid. So here represents the surface of the liquid, and we have a whole bunch of water molecules in the liquid phase, and then above we have water molecules floating around in the gas phase. What happens when you start including a certain amount of solute, for example sodium chloride, is these giant big blobs of salt are getting in the way of the water from boiling because there's less in the vapor phase. So with sodium chloride getting in the way, you have less water in the vapor phase, you have a lower vapor pressure. This has a result of increasing your boiling point because you need to add more thermal energy into water in order to get more and more of those water molecules in the gas phase. When you finally get enough water into the gas phase, at that point it will start boiling when it has reached atmospheric pressure. So without sodium chloride, it's a lot easier. With sodium chloride, it's more difficult, so the temperature of boiling has to increase. So maybe you incorporate a whole bunch of sodium chloride, and instead of boiling at 100 degrees, maybe it boils at 110 or something like that. So let's take a look at how to calculate this. And we're going to calculate the change in boiling point using this equation. Our delta T sub B is equal to K sub B times M, where delta T sub B is our change in boiling point temperature, K sub B is our boiling point elevation constant, and M is molality. The vapor pressure lowering and boiling point elevation both depend on the amount of particles. So again, if you have more particles, you have a lower vapor pressure, which results in a higher boiling point of the liquid because you need to add more heat energy to get more into the gas phase to reach atmospheric pressure. Let's do a word problem now. For example, 11. Here we have a situation where we have a solution prepared from 2.22 times 10 to the third grams of ethylene glycol, abbreviated EG, which weighs 62.07 grams per mole, which we could get from the periodic table. In 2 times 10 to the third grams of water, 18.015 grams per mole. If water is considered the solvent, what is the boiling point of the solution? Now, K sub B, the boiling point elevation constant for water, is given to us as 0.512 degrees Celsius per molal. And that value is taken from a table that looks something like this, where we have a series of solvents and we have their pure, or the boiling point of their pure solvent. So water, as we have seen before, boils at 100 degrees Celsius, but maybe something like chloroform boils only at 61.26 degrees Celsius. We saw earlier, something like chloroform only has dipole-dipole interactions, so it is easier to boil, whereas water has hydrogen bonding, it's more difficult to boil. Along with our boiling points, we also have our boiling point constants. Later on, we're going to talk about freezing points, which we have here, and constants associated with those, which we get from the same table. So here we have our boiling point elevation constant for water. It's 0.512. So in order to solve for how much our boiling point solution is going to change by, we need our delta T sub B. In order to get delta T sub B, we need our molality. In order to get our molality, we need moles of solute and kilograms of solvent. And we can get that all from our equation for molality. So in order to solve this, we need moles of solute. So we have 2.22 times 10 to the third grams of ethylene glycol, and we can figure out how many moles that is by dividing by the molecular weight, or multiplying by 1 over. So that's 1 mole of ethylene glycol is equal to 62.07 grams. The grams of ethylene glycol cancel with grams of ethylene glycol, and we are left with 35.77 moles of ethylene glycol. So we have our moles of solute. Now we need our kilograms of solvent. We have 2 times 10 to the third grams. We divide by 1,000 grams. Our grams of water cancel with grams of water. We're left with 2 kilograms of water. So 35.77 moles of solute divided by 2 kilograms of solvent give us a molality of 17.9 molal. We can then calculate how much our boiling point is going to change by taking our boiling point elevation constant for water, 0.512, multiply it by our molal. So we have 0.512 degrees Celsius per molal times 17.9, which we just calculated. Molals cancel, and we're left with a change of 9.16 degrees Celsius. Now here's the part that's important. We need to know that our delta for this should be positive because we're increasing our boiling point. So the boiling point of our solution is going to be equal to the pure boiling point of the solvent plus our change, how much our boiling point elevation has changed by. So we're going to take boiling point of the solution is equal to the pure solvent plus delta T sub B. The pure solvent, which we get from the table, is 100 degrees Celsius for water. That's just the boiling point of water all by itself, and it's increasing by 9.16 degrees Celsius after ethylene glycol has been introduced, and we are left with a predicted 109.16 degrees Celsius. So that is our predicted value of what temperature this new solution is going to boil at once we've introduced a whole bunch of ethylene glycol into water. In our next example, we're going to talk about how freezing point changes as you include a whole bunch of solute. So in this diagram, what we can see on the left side is our water molecules kind of coming together to form ice. So this is a much, much more structured environment, whereas on the right side, we have a whole bunch of water molecules that are in liquid, so it's a lot more chaotic over here. So as we go from right to left, this is the freezing of water. We have liquid water. As it becomes colder and colder and colder, it starts coming together and forming regular patterns with an ordered structure of ice. As you introduce solute, these big clumps of sodium chloride, they get in the way of the water finding itself. So as you incorporate more solute, it becomes more difficult for water to find itself and freeze and form an ordered structure and form ice. So while normal water freezes at 0 degrees Celsius, as you bring in something like sodium chloride, you actually have to go to a lower and lower and lower temperature to force that ice to find itself and shove out the solute molecules, get the salt out of the way. So that is why we have a freezing point depression. Solutions freeze at lower temperatures than their pure liquids, and this is because of the solute getting in the way of the ordered crystalline arrangement from forming. So we have a similar equation to boiling point elevation, and this is simply describing how the freezing point changes as you increase the molality. So delta T sub F, which is our change in freezing point temperature, is equal to our freezing point constant times molality. And let's take a look at how this works in example 12. So what is the freezing point of a 1.85 molal solution of a non-volatile, non-electrolyte solute in nitrobenzene? So again, from our table, we have information about nitrobenzene, its freezing point, and its freezing point elevation, depression constant. So the freezing point of pure nitrobenzene is 5.67 degrees Celsius, and our freezing point constant is 8.1 degrees Celsius per molal. Given to us is our molality, which is 1.85 molal, and we can then solve for delta TF, which is equal to K sub F times M. So 8.1 degrees Celsius per molal times 1.85 molal, our concentrations cancel, and we're left with a change of 15 degrees. Now we should be going to a lower freezing point because it's a freezing point depression problem. So our freezing point of our solution should be less than our pure solvent. So let's see if it is. We have a freezing point of our solvent minus delta T sub F. So the freezing point of our solvent, nitrobenzene, is 5.67 degrees Celsius minus 15 degrees Celsius is equal to -9 Celsius. In the next problem, this is more of what you would actually see in a laboratory setting, where you have some amount of solute and what you're observing is a change in freezing point. And you're going to back calculate and figure out what is the molecular weight of this unknown solute. So we have a solution that's 4 grams of solute dissolved in 55 grams of benzene, and it is observed to freeze at 2.32 degrees Celsius. That is all the information that we have, and we're going to be able to calculate the molar mass of the compound, the solute. So benzene from that table has a freezing point of 5.5 degrees when it's just benzene, when it's pure benzene, and we have a freezing point constant of 5.12 degrees Celsius per molal. And we can use our freezing point solution equation. Here is what is observed. This is the observed value that we get from the problem, and that's equal to the pure solvent minus our change in freezing point. So we have 2.32 degrees Celsius is equal to 5.5 degrees Celsius minus this change. And so turns out that the change is 3.2. The pure benzene has dropped by 3.2 degrees Celsius to give us our final freezing point. So we can then take our delta TF and use our equation with the constant to solve for molality. So that change, 3.2 degrees Celsius, is equal to our constant from the table, 5.12 degrees Celsius per molal times molal. And we can solve for molal, and we get 0.63. And that value, 0.63, is going to be equal to moles of solute divided by kilograms of solvent. So our moles of solute, we can rearrange, is going to be equal to molality times kilograms of solvent, which is equal to 0.63 times 0.055 kilograms of benzene, and that came from the fact that we have 55 grams of benzene. And we multiply those values together, and what we're left with is 0.035 moles. We have 4 grams of solute, and we know that that equals 0.035 moles, so we can now solve for our molecular weight, which is equal to grams per mole, which is equal to 4.00 grams divided by 0.035 moles, which is equal to 110 grams per mole. This does not give us our exact identity of the compound, but it is a critical piece of information for figuring out an unknown. And that's where we ended today.